let's move on with the next talk. Sandeep Silwal will be talking about improved approximation for hard graph problems using predictions.
So, hi everyone. Thank you so much for being here. This is joint work with Anas, Justin who's here, Siddharth, and Hao. So our paper falls under this umbrella of algorithms with predictions or learning augmented algorithms. So I guess just let me give you a brief motivation of this subfield. The way I view it is it's a relatively new way to do beyond worst case analysis. And what we do is we think of having extra information about the input to help us design better algorithms. Okay, and I'll be more precise in our context. But you can imagine this extra information can come from historical data sets, for example, past inputs that you've seen. Okay. Our paper focuses on a particular class of problems, in particular NP-hard problems for graphs. And there have been many. This is like there have been many nice papers recently, which I'll talk about in a bit, that also study this. Okay. So now let me talk about a concrete problem. Throughout the talk, I will focus on the vertex cover problem. So we call the vertex cover problem. We're given a graph, and we have a constraint per edge. So the constraint is that every edge needs to be covered. And what we want to do is we want to select a small subset of vertices to cover all the edges. Okay. So for instance, this is the picture on Wikipedia, which I kind of think was kind of funny. In general, our paper studies other graph problems where we have a constraint per edge. Now, how do we do beyond worst case analysis? Well, we assume access to the edge predictions. Okay, we assume access to more information to design better algorithms. What exactly do we mean by more information? We're going to assume that every constraint gives us a little bit of information. Okay, so in our case, every constraint corresponds to an edge. So we're going to assume every edge is going to give us two noisy bits corresponding to each of its endpoints. Okay? So for every edge u comma v, we get 2 bits. What do we know about these bits? Well, they're going to correspond to the true, let's say, some true underlying assignment or some optimal assignment in the vertex cover problem. Okay, so 0 means it's not in the vertex cover. 1 means it is. But we're going to assume that the information is almost noisy. So for some parameter epsilon, let's assume it's known, every bit is equal to the right assignment with probability 1/2 plus epsilon. Throughout the talk, let's just assume all these bits are independent. Okay? And then, but we can relax that slightly. So you can see like epsilon kind of represents the quality of the information we have. If epsilon 0, then it's complete random noise, right? Because it's generated. But as epsilon increases, then it's like we're getting more and more power. And you might wonder like where is this prediction coming from? I don't really, in practice, I don't have a good answer, but I think as we'll see, like it's going to reveal something interesting about the problem itself. Yeah.
So like since they are different, the different information can be inconsistent. Right?
Yeah, exactly. Yep. Okay. Yeah. So you can imagine, like, for one way to do this is like first you write down the true information and then you like randomize all the bits. That's another way. So really, like our paper is inspired by some recent very nice line of work which study vertex predictions. So they study some other graph problems and some other constraint satisfaction problems where we get some information per variable rather than per constraint. Actually, yeah, there's many of these authors are here. Ali is here. I think some of them. Yuri should be here. Oh yeah, Yuri's okay. Great. All right. So before I tell you about the vertex cover problem, I'll tell you about that high-level algorithm design principle that's guiding all of our work. Okay, and it's a very simple concept, which is why I really like it. But we'll see later that it introduces some complications. So let's say this is our input graph, and we want to solve the vertex cover problem, right? So of course, 10 is the, or you really want to keep the, you want to take the vertex 10 and maybe some other vertices as well. So like I said, every edge is, we have 2 noisy bits per edge. So I'm not, Wi-Fi wants to connect. I'm not drawing all the predictions, but you can imagine, right? Every edge comes with two bits. So the first step, right, because we get information per edge, right, it's very natural to look at high degree vertices because they have a lot of information attached to them, right? They participate in many constraints. So of course, right, we should be exploring that. So first we identify high degree vertices. Like I said, these are the predictions of the edges attached to the vertex 10. And let's say the second bit corresponds to 10, right? Some of them are, many, all of these bits are noisy, but if we aggregate information, right, there is some slight information. So if, it's natural to say, okay, what happens if we take the majority of these bits, right? For high degree vertices, that should give us a very good answer. And indeed, right, for vertex 10, the majority bit is 1, so let's say, oh, that's a good vertex to take in a vertex cover. And then, right, it's natural, so once we figure out that part of the graph, well, we can remove it from the graph, and then somehow the graph becomes much nicer, right? We've removed all the high degree vertices, so we end up with a bounded degree graph. And in many of these problems, there are much better algorithms than worst case algorithms if we assume the graph has bounded degree, okay? So like I said, this is the high level framework that's guiding all of our algorithms. Like I said, maybe we say, okay, high degree means there's some threshold of degree. For high degree vertices, we take, we aggregate information, we do something with them, we take them away from the graph, and then now we're left with a much simpler graph, and then we do something else. Okay, so this is the high level algorithm design principle, and I'll be more precise about the vertex cover problem, but just to show you intuition of like how can these edge predictions even help. Okay, so like I said, right, these are the main guiding principles, and another way that we view it is like it's these edge predictions give us a way to transform arbitrary worst case input to one that's much nicer. So in some sense, it's doing a reduction between arbitrary inputs to bounded degree through the help of these edge predictions. Okay. Like I said, there's many details I skip, right? What does high degree mean? What does it mean to run like an appropriate algorithm in the bounded degree case, and so on? But these will be problem dependent. But this is like the abstract, algorithm framework that you can, take away from all these algorithms that we have. So now that I gave you a template of how to design algorithms, let me tell you some problems associated with the template. One is false positive vertices, right? Which is we look at high degree vertices. We take the majority of their bits, the bits that are attached to them. There could be many high degree vertices, but for the vertex cover problem, for example, the actual answer could be very, very small, right? The actual number of vertices participating in the cover could be small. So what that means is we could actually have a lot of false positive vertices, which blows up the size of the solution. So here's a simple example. Let's say I have a bipartite graph, right? The cover is really these 3 vertices. Let's say this is my threshold for high degree. I'm just making something up, right? But on the right-hand side, I have many more vertices, and each has some fixed constant probability depending on epsilon and delta of being of me saying, oh, this actually looks like it's in the vertex cover because the majority bit actually ends up being 1, right? But the right-hand side can be unbounded, so this leads you to a big blow up in the number of vertices, even in the the vertices that you take in the cover, even in the very first step, right? So even in the step where you say, for high degree vertices, I'm going to aggregate their bits, I can already blow up the size of the solution. The other major issue is false negative vertices. So there could be vertices that are actually in the vertex cover. They're high degree. But right, it's a randomized process. There's some small probability that I'm going to say, oh, that's not in the cover. If I don't keep them, then I might not even satisfy all the edge constraints. So if, in the vertex cover problem, imagine my graph now looks very different, right? It's a collection of disjoint trees. And, all of these, all of these vertices should be in the cover. But for any one of them, I have some fixed probability of saying, oh, they're, my predictions say actually they're not in the cover. Okay, so we have to deal with that. And not so much for the vertex cover problem, but for other problems we study, there's also an issue of combining 2 algorithms. So what do I mean by that is, right, for high degree vertices, we're essentially listening to the prediction, and for the low degree vertices, we're running maybe some other complicated algorithm. We're actually combining them might conflict with each other for general constraint satisfaction problems. Okay. So now let me talk about our results. Essentially, using the same algorithmic framework, we are able to go beyond worst case analysis and get something that's slightly better than known hardness of known barriers in approximation algorithms. Okay, so it might not look like a big improvement, right? Like this is a very mysterious function, but if you imagine epsilon equals 0.0001, it's a little bit smaller than 2, and that's like the main point, right? You can 2, you can't do better than 2 unless p equals np, I think, and now you can do a little bit better with the operations. So now let's see this algorithm design framework in action. Okay. Yeah.
Go back a slide.
Yeah.
So the best bound is actually not 2. There is a bound which is 2 minus function of delta.
Exactly. Yeah.
Delta function looks exactly like
exactly. Yeah. So that exactly is what I'm going to get in a bit, but that's exactly what's happening, right? Like I said, we're going to be able to transform general inputs to one that looks like bounded degree case, and the delta you plug in is roughly going to be the high degree bound. Yeah. So let's start with this framework that I just talked about. And it makes sense, right? In sublinear algorithms or in sampling, right? We set the high degree to be 1 over epsilon squared, because that's when you start getting like concentration. So let's say we fix some high degree threshold, and we do the following natural approach, right? For high degree vertices, we take them, we aggregate their information. If it looks like they're in the if it looks like we think we should add them to the cover, we do. Otherwise, right, we want to solve the vertex cover problem, we add their neighborhood instead. And then we remove all the high degree vertices from the graph, and then we run another low degree solver on the remaining part, okay? So this is a very natural idea, right? This seems promising. All the edges are covered, right? This will actually be a solution to the vertex cover problem. For any fixed high degree vertices, the probability that it's that my aggregated information is correct is very, very small, which seems awesome. And like we just talked about, there is a better algorithm for bounded degree groups, right? And that means like on step 5, right? If I can pretend to plug in delta, whatever this is, then I do get a better approximation. Now let's talk about the analysis, like how many vertices do we actually need, okay, to be in the cover, right? We want to compete with opt, okay? So the false negative case in this problem turns out to be very easy. So what is a false negative? False negative is a vertex that should be in the optimal cover. Let's say it's a high degree vertex, but we predict it to not be in the cover, right? What do we do then, right? Well, we then, if we predict to not be in the cover, we take all of its neighborhood. But the probability that we predict incorrectly, right? We have, for high degree vertices, it's sort of proportional to the size of the degree, so it's very good, right? The expected number of these extra vertices that we add in this step is very, very small, okay? Right? Like x times e to the negative x is a very small value, so that means we can charge to opt, right? Like for any false negative vertex, it has that was an opt. We didn't include it; instead, we included its neighborhood. But the whole expected number of bad vertices that we added in this step is very small. Okay, so this is the case. The hard case turns out to be bounding false positives. So let's say a vertex is not in the optimal cover and it's high degree, but we mistakenly think it is, right? The information we get is noisy, so this can happen, and it can happen very often, right? And actually, our algorithm should be robust to this case. Otherwise, like it doesn't, this is not a natural model to say. So the cost we pay is, just adding this vertex. Again, right, it's a high degree vertex, so we're actually fairly confident that this won't happen, right? It's not in the cover, but we think it is. But the problem is like opt could be very small, but where the expected number of extra vertices we get is proportional to n, right? N and opt are not necessarily related to each other, right? So it could be that, right, for any vertex that's not in the cover, there's a small chance that we think it is. If we add all these vertices, we get theta n. So then we can get a bounded competitive ratio. So we need new ideas, and so this is my dog. So I like it did not. When I told her this algorithm, she was very unhappy. So so far what I've talked to you about is like we haven't used any structure of the vertex cover problem, right? I've been talking in a very abstract way about edge, problems about graphs and edges and so on. But now let's focus on the vertex cover problem. So what is one nice thing about the vertex cover problem? Well, it's a very simple observation, which is, if a vertex is not in the cover, all of its neighbors must be in the cover, right? Otherwise, you won't cover the edges, right? So it's a very simple observation. So what are we going to do? We're going to design a new way to charge the cost of our algorithm. So not to get an n factor at the end, but to get an opt factor at the end. Okay, so the charging scheme is going to be interesting. So the algorithm is still going to be very simple, but the charging is going to be interesting. Okay, so what are we going to do, right? Take a vertex that's a false positive. We want to charge it to one of its neighbors. And we know all of its neighbors are in the cover, so that seems good. And particularly, we want to charge it to a neighbor whose degree is strictly smaller than the vertex degree. Okay, so ideally, I want to take a false positive vertex, charge it to a neighbor u whose degree is smaller. So there are two questions: what is the total charging cost? And the second, maybe more important question is: what if you can't do this, right? What if all the neighbors have larger degree than me? Then I can't do this charging scheme. Let's and then so when I was we were stuck, and then actually maybe our dog inspired us by after taking a good nap. Anyways, so I get just to draw in pictures, right? If I have a false positive, I actually somehow want to charge it to one of the true vertices in the cover. So what is the total charging cost? Well, one way to count this is, consider a vertex in opt, right? How many times is it charged? Okay. So some other vertex is in its neighborhood, like a false positive, charges this vertex if the following three things happen, right? One is like, this degree has to be larger, right? That's how I define how I charge it. Of course, right, this is a false positive vertex, so it has high degree, and I actually mispredicted for this vertex, right? So all of these events have to happen, right? I had a high degree vertex that's not in the cover, I accidentally thought it was in the cover. Well, the expected cost charged to a true vertex in the cover is, it's size of the equivalence times this probability, okay? Now this probability is small, and the reason is because of this condition, right? I only charge to a vertex in opt for only things that have larger degree, but those things have a very small probability of misprediction. So somehow this can cancel with this now, where previously it couldn't. So does that make sense? Like, for a vertex that's actually in the cover, how many times can it be charged? Well, it can be charged by all of its neighbors, but the neighbors only charge it if they have a higher degree, and then we use the probability of mispredicting for them. So then we can say, okay, the total sum of charges, right, is sum over all the vertices u that are in the cover, and that's small compared to opt. So then we're happy. So the charging is actually very simple. Somehow it's not doing any work, right? I haven't changed the algorithm yet, so that seems bad. But if I could find, for every vertex v, a neighbor that's in the cover that has a smaller degree, then this whole scheme works. But what if there is no such vertex u? This is where we start changing the algorithm. Well, right, imagine a false positive vertex. If there's any neighbor that has a smaller degree, then I'm happy. Okay, then the algorithm works. Without knowing it, right, the algorithm just works. But what if all the neighbors have higher degree than me? Right? Well, all my neighbors are actually in opt. So there's two cases, right? One case is if there is a neighbor, if I have a neighbor who was also mispredicted, then actually I was already counted under false negatives. Right? The reason is, right, if I had a neighbor who was mispredicted, right, I know all my, this Wi-Fi is really annoying. If I had a neighbor who was mispredicted, I know all my neighbors are in opt. But if the neighbor was mispredicted, right, what did I do in my algorithm? In my algorithm, I added the entire neighborhood, right? If for a high degree vertex, if I thought it was not in the cover, I added all of this neighborhood. So I already counted v in this case. Okay. So just to summarize, I'm a false positive vertex. If all my neighbors have high degree, then I either already, I'm already good, like I already got counted in their false negative count, which I bounded before, or I know that all my neighbors also have their majority bid to be 1. Okay? If their majority bid was 0, I already got counted in the false negative. So, well, right, then now this is where we change the algorithm, right? Now when I run the algorithm, if I notice, for a vertex, I predict it to be in the cover, and for all of his neighbors, I also predict it to be in the cover. Why would I add this vertex, right? It doesn't make any sense. So I actually skip adding it. That's the first modification to the algorithm. We're going to do a sensible step where if I look at the prediction, I have a vertex, it should be in the cover. Let's say the prediction says that all of his neighbors also should be in the cover, then why would I add the vertex? So I actually don't add this vertex to the cover. So that's modification number 1. This causes some slight issues where all the edges may not be covered. So I can imagine a case where I'm a vertex, all my neighborhood looks like it should be in the cover, so I don't add this vertex. But for my neighborhood, they also have their neighborhood that looks like it should be in the cover, so you don't add them. So there could be some edges that are not covered. But later, you can do a cleanup step where, at the very end of the algorithm, if you look at all the edges that remain, you can run another, you can run the algorithm just to cover them at the very last step. Okay. So yeah, these are the only 2 modifications to the high-level, algorithmic template that I presented. And in full glory, this is what the algorithm looks like. It's pretty much the same, right? I get inputs at my predictions. I set a high degree threshold. That's roughly 1 over epsilon squared. For all the high degree vertices, I take their majority bit. If it looks like it should be in the cover and all the neighbors are high degree, and they're also in the cover, then I actually skip the vertex. I don't add it. Otherwise, right, I add the vertex. If it's not, if it's predicted not in the cover, I add the neighborhood, right? So it's the same algorithm except I do this skipping step. The other modification is like now some, edges that are adjacent to heavy vertices or heavy light vertices may not be covered. So I just run the standard factor of 2 approximation algorithms on these sort of like edge cases. Turns out there aren't too many of them. You can bound that, so this doesn't, harm us at all. And finally, right, our graph is a bounded degree graph, right? Degree bound is 1 over epsilon squared roughly, so I can run this better algorithm that exists for bounded. So just to summarize, right, the algorithm is very simple. We just do very natural steps, but somehow the charging scheme I think is very nice. Like you have to be clever in charging to opt. You can never charge to n because once you do that, like you're gonna fail. So if we carefully combine these ideas, it proves this result, and somehow similar ideas are useful in proving all these results as well. So it's not really about different results. I think it's really about the template that's powerful. So in conclusion, we introduced a new model of edge predictions. And generally, you can think of a model where you have a constraint satisfaction problem and you get a constraint per edge rather than, let's say, per variable. So you get more power and hopefully you can do something with that power. Of course, there are many open problems. I think the most natural one is, like I mentioned before, there are some very nice series of works on vertex predictions, like you get prediction per vertex. For us, we get more power, right? We get more information, but somehow that also gives us better algorithms. So the question really is like, can we quantify the power of these prediction models? Like, how are they related to each other? Are there reductions? Can we prove lower bounds in this setting? There are some tools to prove lower bounds, but their lower bounds are like relatively weak compared to the upper bounds. And whenever I tell people about this model, like some people are very unhappy to think, hey, this model is like too powerful. Well, then I actually that's very I actually like it when people are unhappy because then we can let's work together to create better models, right? But my personal opinion is like I like any model that introduces new ways to look at even old problems. And then that's when I'm happy. But yeah, so please see our paper or come talk to me or Justin afterwards for other details, and we even have some experiments. So. Thanks.
Hands or question? And the next speaker. Yes.
Yeah.
So you use independence pretty heavily to make all those turn-off bounds work, right? Have you thought about any kind of bounded independence setting that this might hold?
Yeah, so in the paper we actually prove things with 4Ys or 3Ys independence. I forgot, but yeah, you don't need, because everything we're getting results in expectation anyways. So yeah, you don't need independence super strongly. With at least 4Ys independence is good.
One more question.
So I think another model of algorithmless prediction is you receive a prediction of the final plan, which can be erroneous or suboptimal. Do you think you have any connection on how this will connect to your model, or you have any idea on this kind of prediction that you might receive?
Yeah, so there are ways to some reduction between simulating one prediction with the other. So for instance, if you receive a solution as a prediction, what you can do is you can flip some of the solutions independently, and maybe that corresponds to vertex prediction or something. So there are some connections, and there are also upper bounds in this new model that you've said. But somehow it's much more work needs to be done because all the upper bounds seem incomparable to each other. You get a very different style of upper bound. So you actually get it. The approximation factor you get depends on the set difference between your solution and what the opposite is. So yeah, I think more work needs to be done to quantify the relationships between all these models.
Okay, that's it.